Hello students, and welcome to the final video lecture for Chapter 9, Section 9.7 Tessellations. Our learning goal for this lesson is to identify figures that tessellate and to identify transformations and translations within tessellations. So here we have two examples of tessellations. By definition, a tessellation or tiling is a repeating pattern of figures that completely covers a plane, without gaps or overlaps. Tessellations can be made using translations, rotations, and reflections. And oftentimes you can find shapes that tessellate in art, in nature, as in the cells of a honeycomb, and in everyday life, like tiled floors. So you can see the figure on the left is a translational tessellation, and the figure on the right is a rotational tessellation. So problem 1 asks us, what is the repeating figure in this tessellation, and what transformation does the tessellation use? So truth be told, this can actually be a fairly complex question to answer, because there are several ways to answer this question. Now the repeating figure in this tessellation is actually going to incorporate several different pieces. So we can see that if we have one turtle and we attach to that one bird and we attach to that one fish, we can actually tile the entire plane using these three shapes. So this is a very complex answer to this question. We can tessellate the entire plane using a tile that looks something like this. Now, if I were a tile maker, I'll be honest, that is not the tile that I would use to tile a floor with this pattern. Personally, I would connect the middle of each of these turtles, and I would use a hexagon tile that has all of these half turtles on the outside, 3 birds, and 3 fish on the middle. So I would use this hexagonal tile as my tessellation. And this could be a translational tessellation. In other words, we take this tile and we just slide it over here and we get the next shape. If we're going to use the one turtle, one bird, one fish concept, then we're going to have to use some type of rotation in order to get it into the other locations. And in addition to that, we're also going to have to use a translation to completely cover the plane. So by definition, the figures in a tessellation do not overlap or leave gaps. So if the figures are polygons, then the sum of the measures of the angles around any given vertex in the tessellation must be 360 degrees. So in these example pictures, you can see that these trapezoids make a tessellation because we have 2 sets of 120 and 2 sets of 60, which does in fact give us 360 degrees. So then you can see in this second example, we have this gap over here, and there's no way that we can get another shape in here that's of the same size. So this is not going to be a tessellation. So problem number 2 asks us if a regular 18-gon tessellates, and to explain our solution. So first off, I've hidden our regular 18-gon right here. So the O of does is actually a regular 18-gon. So first, we know that all of the angles of a regular 18-gon must have the same measure. So going back to what we learned in polygon angle sum theorem, we know that each angle has to measure n minus 2 times 180 divided by n. And if you plug n into this formula, you'll find that each angle measures 160 degrees. Which was our second step of this problem. So each one of these angles is a 160 degree angle. So then the last part of the question asks us, is there a multiple of the result that equals 360 degrees? So we take 160 and we add 160 to that. And 160 times 2 is 320. So this is less than 360. So the only thing that we can do is try to add another 160 to this. And unfortunately, we get to 480, which is now greater than 360. So the answer to this question is no. So the answer to does a regular 18-gon tessellate is actually no. And the explanation, we would say there is no multiple of 160 that is 360. So please remember that a figure does not have to be a regular polygon to tessellate. In fact, every single triangle and every single quadrilateral tessellates, as you can see below. So with any given triangle, not necessarily an equilateral triangle, if you take 2 copies of the first angle and make them vertical, 2 copies of the second angle that are vertical, and 2 copies of the third angle that are vertical, you can tessellate the plane with any triangle. The same thing is true for quadrilaterals. You take 1 of each angle at every single vertex, and since the sum of every quadrilateral is 360, you get that every single quadrilateral can tessellate the plane. So you could create some very interesting tiling patterns for floors. So every tessellation has at least one type of symmetry. The tessellation with regular hexagons, which is seen below left, has reflectional symmetry in each of the blue lines. It has rotational symmetry centered at each of the red points. And in addition to that, the tessellation has translational symmetry and glide reflectional symmetry as seen below center and below right. So problem 3 asks us to determine what types of symmetry this tessellation has. So the first question that we have to ask ourselves is, does it have reflectional symmetry? In other words, is there any line that can be drawn that if I flip it across that line, it's exactly the same thing? So I start by trying to draw lines that would create potential reflectional symmetry, and you can see that every potential line that I draw could cut one triangle into half, but the other triangles don't get cut in exactly half. So this figure does not have reflectional symmetry. So let's see if it has rotational symmetry. Okay, so for rotational symmetry, I need to find an angle less than 180 degrees that will map this onto itself. So as I start to spin this thing, I'll notice that as I get to a certain location, I can actually get it to line up onto itself perfectly. So this figure does have rotational symmetry. It has 120 degree rotational symmetry. So the next type of symmetry we'd like to check is translational symmetry. And so what I like to try to do is take this and slide it to another location and see if I can make it work. And you can see that there are a lot of places that I can slide this figure that it'll copy perfectly. So this figure also certainly has translational symmetry. And finally, let's check to see if it has glide reflectional symmetry. So is there any way that I can slide this figure both down and flip it across the line so that it will line up on itself? So if I flip this, I should be able to flip it and then slide it so that it lines up somewhere. And because of the location of that medium-sized triangle now, it seems like I'm going to run into a bit of a problem. So this figure does not seem to have glide reflectional symmetry whatsoever. And that concludes section 9.7 tessellations. Hopefully you understand what properties of a figure causes it to tessellate, and you're able to identify the different transformations and translations in tessellations. Thanks for your attention, and I'll see you soon.